Okay, this is part 2 of section 4.2, graphing polynomial functions. Okay, so in the first section we talked about the maximum number of real zeros, maximum number of x-intercepts, and turning points that you could expect. And we kind of use that to sketch the graph of these polynomial functions. Okay, well in this part of this section we're going to talk about the graph a little bit further, and we're going to talk about a method for finding where x-intercepts may be hiding, or where some real zeros may be hiding. Okay, so let's see. I'm going to start off with an example here. So example 1. Here's a function, f of x equals 3x squared minus 2x minus 11. Okay, and I don't know much about this graph. Okay, I do know that it's squared, so it's a parabola. It's going to look something like this, right? But I really, without solving this, I don't know where these points are, okay? I might have a good idea of where they might be, but I don't know where they are. So one thing I may want to check is maybe, just maybe, let's see, this is 2 and this is 3, right? Maybe they have this point right here is between 2 and 3. Okay, well, again, I don't know what this graph actually looks like. It could look like that. It could be upside down. Who knows, right? But there is something I can do. I can actually plug in 2 into the function. Okay, get an answer. I'll type that in my calculator and get -3. I can type 3 into the calculator. And typing that into the calculator, I get 10. And so what does that mean, right? That means that this is 2 comma -3, and this is 3 comma 10. So I know that 2 comma -3 is a point of that graph, and 3 comma 10 is a part of that graph, a point on that graph. Well, it's pretty obvious now, just looking at these 2 points, that somewhere in between 2 and 3, it has to have crossed the x-axis, right? It's the only way it can get from being down here to up there. Okay? So we can conclude then that there exists a real zero, or an x-intercept, between 2 and 3, where x is 2 and x is 3. Okay, well, what we just did is called the intermediate value theorem. Okay, it's a method of plugging in 2 values where you think there might be a real zero or an x-intercept between them. You plug them both in, and from there you determine positive or negative. If there's a positive and a negative, then you could say, oh, okay, it had to have crossed the x-axis in between those 2. Again, that's called the intermediate value theorem. Okay, or we'll call it the IVT for short. Okay, so there we go. We used the intermediate value theorem and we determined that there was a real zero between 2 and 3. Okay, not actually having to picture the graph. Okay, well, let's do another one. Okay, so example 2, we have the function f of x equals 2x to the 5th minus 7x plus 1. 2x to the 5th minus 7x plus 1. Yeah. All right, so, and I just want to know, is there a real zero or an x-intercept between x equals 1 and x equals 2? Again, I don't know what the graph looks like, especially this x to the 5th power. So I want to know between 1 and 2, does it cross the x-axis? Okay, well, I'll use the intermediate value theorem. I'll plug in 1. 2 times 1 to the 5th minus 7 times 1 plus 1. Type that in the calculator, I get -4. So I'll plot that. It's around here somewhere. Let's plug in 2. 2 times 2 to the 5th minus 7 times 2 plus 1. That's going to be a 51, a positive number. So we have something way up there. So we have a negative, we have a positive. Okay, well, the only way for me to get from this point down here to this point up there is to cross the x-axis, right? So we could conclude that there exists a real 0 or an x-intercept, right? Same idea. Between x equals 1 and x equals 2. Okay, well, what happens if they don't end up being the same? So let's do another example. One more example. F of x equals 3x squared minus 2x minus 11. And I want to check to see if there's a real 0 between 2 and 3, when x is 2 and when x is 3. All right, so 2, 3. I'll plug in 2. Okay, plugging in 2 will give me if I can find it. You know what? I think I did that one already. I sure did do that one. All right, so we're going to change that. My fault, writing down the same example twice. There we go. Okay, so it's going to be x cubed plus 3x squared minus 9x minus 13. And I'm checking between x is 1 and x is 2. All right, there we go. That's better. Okay. So let's plug in f of 1 equals 1 cubed plus 3 times 1 squared minus 9 times 1 minus 13. And that gives me negative 18. Down here somewhere. F of 2. 2 cubed plus 3 times 2 squared minus 9 times 2 minus 13. That gives me negative 11. So not as far down as negative 18, but there we go. All right, so now we have 2 negatives. And by the way, the same would be true if we had 2 positives, okay? But what can I conclude? Can I say that it doesn't cross the x-axis? I mean, maybe it doesn't. Or maybe it does cross the x-axis, right? Maybe it follows some kind of shape like this. I can't tell, right? I don't know which one of those 2 shapes accurately reflects the actual graph here. So I would just say that the intermediate value theorem is inconclusive. Inconclusive, right? Or we can't make that determination. We don't know, right? We can't tell by that information. So the trick to the intermediate value theorem, either it confirms that there is a real 0 between those 2 x values, or it's inconclusive. It will never tell you no, that there is not a real 0. You can't tell that, okay? All right, so there we go. That's all there is to the second part of section 4.2.